Welcome to part 3 of the chapter on aminoglycoside dosing and drug concentration predictions. In this video, we will use the pharmacokinetic parameters we calculated from the measured concentrations in part 2 to design a new dosage regimen intended to produce desired peak and trough concentrations. I hope you enjoy the video. We will now continue patient case 2 from part 2 of the aminoglycoside dosing. Using the pharmacokinetic parameters calculated from the measured concentrations in part 2, determine an appropriate interval and then dose to produce a peak of 8 milligrams per liter and a trough between 0.5 milligrams per liter and 1.5 milligrams per liter. Remember, the peak will occur a half an hour after a half-hour infusion, and the trough is to occur a half hour before the next dose. The previously calculated parameters were a K of 0.084 hours to the minus 1, a half-life of 8.3 hours, and a volume of distribution of 21.64 liters. Let's begin by determining the interval range. We know this equation, K equals natural log of Ci over C divided by time change. We've used it quite a bit already. And what we need to do to determine an interval is shift it around. We'll move T change to the left and elimination rate constant K into the denominator. It's important to remember that T change is what a dosage interval is. It's the time to go between concentrations. So let's solve for the first one. We want to figure out the range. The peak is desired as 8 milligrams per liter, and the highest possible trough is 1.5 milligrams per liter. If we divide that by K, it gives us an answer of 19.9 hours to go from 8 to 1.5 with a K of 0.084. But we also have to remember to add 1.5 hours to the interval, because we're going to infuse over a half an hour, and we're going to allow another half hour to elapse before we collect the peak, and we're going to collect the trough a half an hour before the next dose. So that hour and a half has to be added to the dosing interval. That gives us a total of 21.4 hours. If we use the lowest possible trough of 0.5, the time it takes to go from 8 to 0.5 with a K of 0.084 is 33 hours. And we also again add 1.5 hours, and that gives us a value of 34.5 hours. So our dosing interval must fall between 21.4 and 34.5 hours to meet the criteria of a peak of 8 and a trough between 0.5 and 1.5 hours. That gives us a potential trough in this range, a potential dosing interval in this range of 24 hours. We can also do it a lot easier than that, using a simpler approach. In this case, you see it takes one half-life to drop from 8 to 4, another half-life to drop from 4 to 2, and another to drop from 2 to 1. Thus, we use 3 half-lives to go between 8 and 1, and 3 half-lives times 8.3 hours is 24.9 hours. So it's really quite easy to figure out the approximate dosing interval just by this simple approach. Now then, we need to determine the dose to produce the desired peak of 8 milligrams per liter now that we've determined that the dosing interval is going to be 24 hours. We use the equation to describe the event once again. We're going to solve for a concentration of 8 milligrams per liter. That's going to occur 0.5 hours after the end of the infusion. And the only thing we don't know is dose. So one approach we can use is fill in all the values and multiply everything on the right side times dose to equal the concentration and solve that way. So let's see it again. If we plug in the numbers with a we can then go and determine the dose. So here are the calculations. The peak is 8 milligrams per liter. That's going to occur 0.5 hours after the end of the infusion. And again, if we calculate everything here times D, that will equal 8 milligrams per liter. So once I do that, everything but D is equal to approximately 0.050. If I move 0.050 under 8 milligrams per liter and divide it into it, I come up with a dose of 159.8 milligrams every 24 hours. We would clearly round that off to 160 milligrams, and because the dose is so close to the predicted, I'm not going to bother to calculate the difference in the peak concentration because it would be so small. Now let's determine the trough on 160 milligrams every 24 hours with a peak of 8 milligrams per liter, because we want to verify that it will fall between 0.5 and 1.5 milligrams per liter. We also want to have a sense of what it might be in case we measure the concentrations. As usual, we need the formula that describes the event, and in this case, the trough concentration is measured 23 hours after the end of the infusion. That goes into this portion of the formula where for capital T, or time after the end of the infusion, that the concentration is drawn. We gave our 160 milligrams and everything else is the same. Once we do that and do the calculations, the trough comes out to be 1.21 milligrams per liter. We can also calculate it using our formula C equals CI times e to the minus KT. What we need to know is the time after the CI that the concentration is drawn. In this case, the trough. The CI would be the peak at 8 milligrams per liter. So the time between those two is 22.5 hours. The peak is drawn at 1 hour in the interval, a half hour after a half hour infusion, and the trough is drawn at hour 23.5, or a half an hour before the next dose. So the 22.5 hours goes in this portion of the equation, and we end up again with a trough of 1.21 milligrams per liter. So either approach can be used, you just have to be careful about the times used. With the full equation, the time after the end of the infusion that the trough is drawn is 23 hours, but when we use the smaller equation, it's the time when the peak was drawn, which is at 1 hour, to when the trough is drawn at 23.5 hours.